Welcome to this last day of this week. I am very sorry, I never realized I was muted all the time. So we are going to start a new topic, and we did do unsupervised learning, introduced it for the 5 or 10 minutes of the last section, the last lecture. Otherwise, we use the time to wrap up the discussion around random forests and trees, and we looked at the lab session. And so the unsupervised learning methods, which we had an overview of early in the semester, will have 2 main topics. And principal components analysis is the first one, and clustering is the second one. So we are on schedule for the most part compared to what we had set out in the syllabus, but we are a lecture or so off from that. So we are going to probably have the clustering topic covered after the midterm. We have 2 days only next week. The 11th is a holiday, and we'll have a midterm on Friday. And so Monday's class would be used for review. If I have enough time, I will start off clustering. Otherwise, we will be doing clustering right after midterm. And that's just a lecture off from what we had set out to do. But I think this was worthwhile what we did last time. So we'll start principal components analysis today. And I'm going to have my warm-up question, and maybe I will ask somebody who is fast to type up the question. And so let me see if I have a volunteer. The question I have is basically this. I want to know if you have seen principal components analysis before. Are you looking at, or are you learning principal components analysis for the first time now? If not, when was the last time you see it in a course, or what context did you see it? And I'm not sure who I would pick, but I'll pick somebody whose camera is on. Brit, her camera is on, so I'm going to ask her. Are you looking at are you learning about principal components analysis for the first time in this course? If not, when was the last time you saw it? In what context was it? And brief answers would be enough. And let me make that a direct connection to what we'll be talking about, and that's our warm-up question. The slides for today are posted, and these were already posted last time, but I posted them with a complete discussion of what we will do for principal components analysis, and they are there on Blackboard. So I'm going to switch there and get that portion of the slides shared, and we will start discussing, and you can go ahead and tell me about your experience with principal components analysis as I do this. Come here. I'm going to go to full screen. Okay, I think we are all set, and then I'm going to have my chat session open so I can follow along. Okay, so one way to motivate this work is to say that unlike supervised learning, where we have labels, we are in the territory where we have data, and we are interested in patterns and interesting discoveries around them. And one of the things that we would want to do most of the time would be to reduce dimension. So principal components analysis would in some ways be called a method for reducing dimensions. I'm not sure if you have heard the word latent features or latent properties or latent something before in some other context. And this is a mathematical way to get to things that are not directly observed, but they are essentially summarizing whatever it is that we are after. So I'm going to give you a fun example. For example, you look at somebody and you kind of decide out of the things that they say or they do, the way they talk, the way they dress, whether somebody is fun to be with, or somebody is, in some ways, some category that you would put them in your mind. After you've seen made some observations around them, you put them in a category that you may think. You've had some analysis, you may not have thought about it, but you have had some analysis, and there are things that you took into account, so you've reduced them into one dimension, and you put somebody else in another category. And that sort of thing mentally happens all the time in what we do. So we reduce dimensions. And much the same way, we could mathematically think about having to look at, data, we're having to look at features, and these features always keep in mind that what you have is, if you think of it as a matrix, you've got your observations in the rows, and you've got your features in the columns. You want to get the essence of it, not necessarily to remove out some things that are important, some things that are not important. No, you are putting them together. And when you have reduced them, then you have fewer dimensions to deal with. And that might be one way to think about what principal components analysis would do eventually. So it's a low dimensional representation of a data set. And it is peculiar. It is unique in the sense that it finds a sequence of linear combinations of variables that have maximal variance and are mutually uncorrelated. We'll unpack this bullet in a couple of slides, and I'm going to give you time to write down notes as you go along. And because I'm not able to write, I'm trying to always try to kind of find visual ways for you to help out every time I make a point. And so the idea I told you, when you look at a person and you have seen some things about them, you are combining them. These variables that you're taking into account. Mathematically now, you're looking for a linear there is different ways to combine variables. Now you're looking for linear combinations of them. So you are adding them up the way they are. And so you are combining. What you would probably be doing is worry about or consider how much weight you would give to each one of them. So that will be the coefficient that you would use. Otherwise, you are linearly combining these variables. And what you are after is try to capture something that would tell you the maximum information. And that maximum information could be said as maximal variance. And then you're going to find a way in which these are mutually uncorrelated. In other words, you're trying to help yourself by having as much new information as possible. One other thing, which will be evident when we finish this lecture today, where principal components analysis would be used, is to visualize, because you have a need for having to say something that involves a lot of dimensions. When they are reduced to fewer dimensions, then you have an opportunity for us to visually see what the data is saying. And that is another good reason why we would want to look at principal components analysis. So let's do now mathematically. The name may suggest, sometimes some names are helpful. Principal components analysis is among the places where a name is helpful. So you're looking at for components. When things are reduced to a lower dimension, you are looking for components. And these are principal in the sense that they are telling us the most about the data set, right? So we will have several of them. And we will start with the first. And order is important. And we will end up finding out that there is actually a natural sequence in which these things are called first and second and third. And that would be revealed by how much information they are going to tell us. So let's start with the first. So the first principal component of a set of features, and we have we have been consistently using P to see how many predictors we have, how many variables we have, and we will still continue to use them, x1 to xp. And so these are our predictors. These are the features. These are the vectors we have. And we're going to look for a linear combination of these. And this is going to constitute our first principal component. And Z1 is the name we will give it. So what is Z1 now in terms of the vectors? We have feature vectors. It's just a combination of them, linear one. And the phi 1, 1, phi 2, 1, and so on is the coefficient that we are associating with them. And we will use this subscript 1 to show that this is the first principal component. And we've got P vectors to combine. And so the coefficients that we're associating with each of these vectors now, we'll call them phi or phi, and we have the second subscript there, 1, showing that it's a principal component, and the first subscript there corresponds to the vector we are looking at. And what do we want this linear combination? There are so many different ways in which we can achieve this Z1, depending on what phis we are using. What do we want it to achieve? We want it to achieve that it tells us that it has the largest variance. That means it has captured the most of the information that these feature vectors are telling us. And so we will want to look for a vector like that, D1. And we will see in the second or third bullets, we will elaborate on this one, but we will choose these values that we are associated, the weights for these vectors when we linearly combine them, such that they're normalized. Why do we want them to be normalized? We want them to be normalized because if I wanted to have a vector that's a linear combination of p vectors, and I am free to choose whatever weight I am going to use, and what I wanted is this one to tell me the largest variance, then I could have made them arbitrarily large. My phi11, phi21, phi p1, I could have made them arbitrarily large, and so that means I would have an easy way, a not helpful one, but an easy way to get this one large. But I can't do that because then there is no way for me to tie this down. And therefore, we need to normalize them. And the way we would normalize is that the sum of this p coefficient that we are going to use will add up to 1. That means now, if there's some after they are squared, then there is a reason why we would square them, is going to add up to 1. What we really are doing is associating different weights to vectors. Now it makes sense. So I'm going to find the thing that gives me the largest variance. That means I'm going to depend on what x1, x2, and up to xp are saying. I am going to linearly combine them, but the weight I would associate with each one of them is normalized. That means now there is a relative importance that I'm pointing to x1 compared to x2 and things like that. And now there is a name, and this name sometimes come from the different fields in which principal components analysis is used everywhere. Lots of things in machine learning, image classification, things that with natural language processing, but in the natural sciences, it's used also in very many places. In the social sciences, it was used in very many places. The toy example I gave you, whether somebody, you could call them, are fun to be with or something like that. You are character, you are reducing people's behavior to certain things. And if this was a measurement you have done around people's behavior, then you actually have social science reasons or psychological reasons to do this. And so it's almost everywhere. And so some of these terms are coming from those types of inspiration. So they're called loadings. They are called the loadings of the principal component, these coefficients. And they together made up a vector, and we have a vector of length p, and because we want to write it in a way that doesn't take us too much space, we write it as a row, but it is a column vector, and that's what the transpose you would see is. Okay, now we did do, the third bullet point is what I told you, why we chose them, the sum of the squares, these loadings to be normalized is because we want to constrain it. Otherwise, we would have had a chance to make them arbitrarily large, and that would not have been very important. So what's the principal component? I have p vectors. I have linearly combined them by choosing coefficients to these p vectors in such a way that the sum is normalized, or the square of the sums is added up to 1. And my insistence on what I wanted this first principal component to achieve is that it tells me the most. In other words, it has the largest variance. A picture would be helpful to explain this. And this is a scatter plot of some ad sampling versus population. And it's not very, very important what these things are, but we've got two things and they're plotted one against another. What you see in the purple lines is what these points would be. And so they occupy this space. And so for population of size 20 and ad sampling of something like 4, you've got this purple point at the bottom, and it goes on that way. So what am I going to look for? The first principal component in this picture is shown with the green line that you see. First of all, it's a line now. It's a vector. It's going in this direction. What it has done is it has captured the variance around this point the best way possible. And just for a second, imagine that this what you just did was a horizontal line, just a line that's going to be along the parallel to the population size. It is, this data set has some distribution around population. It has got some distribution around the ad sampling. There is something that the population variance is telling you. There is something that the ad sampling variance is telling you. So what this new line now tells you is if I combine this to the most of the variation in this data could be explained along the green line. The horizontal line would not have told us all that much about that variation because we would not have captured what is being varied on the ad sampling size. So some combination of them is what is being captured, but this is the best. And you can see this line is not tilted so much to the vertical. It's much like towards the population, and it kind of makes sense the way you see it. So among all the possible lines that you could draw, that would capture the maximum variance with this, the best way to, that has got the largest variance, the best representation of what the data is, would be that green line. And it's a unique one. We'll come to a point where we will have to find out, we'll mathematically say how we will compute it, how we will find it. But this line makes sense now to see how much of the variation is explained by that green line. Forget about the blue line for a second, but that's actually the second principal component. And we have two components here to begin with. There's only two p's we have. P is equal to 2, and so we cannot have more than 2, so we get exactly 2. So we have now represented this data. We didn't reduce the dimension because it was 2, and we just are in 2, but we have this representation. So now, if I was going to see the phi's, the loading vectors, those values would actually be the way the points are away from that green line. That will be the phi1, phi2, and so on for each one of these vectors. But now I have been able to find a line that tells me the most, that represents the largest variance, and that will be the green line. Okay, and so this is a pictorial way of looking at what the first principal component would be. So let's see now how we would compute it. So we will generalize, and so we will call our X, our data set, n by P. N is how many points we have, how many rows we have. P is the vectors we have. We are interested in variance, and so we're going to make a simplification and to see what mathematical reality will help us compute this. To do that, we're going to assume that it is centered, each of these x's has been centered to have mean 0. That's the columns of x are, the mean of them is 0. We will, when we wrap up this discussion, we will learn that we are in a position to do that when our data is not given that way. So we are now describing how we get to a place where we will compute this. But if our data is not like this, then we will make it this way so that we have some desirable features. So let's assume that this is true, that the mean is 0. And so now we have a way to talk about variance in a much simpler way. And so what we're looking for, and we will make the Z, the capital Z was the first principal component, we're going to look at them piece by piece. And so the first component of it, the I1, will be written this way. So this is an element-wise description of it. And so the variance now will just be, because the mean has been reduced to 0, will be the summation of this will be equal to 1. That's the constraint we have put on the coefficients. And since each xij has mean 0, now the variance is going to be the sum of these zi's, the way I have described them, squared them, add them up, and divide by n. That will be our variance. Okay, so if now I have each of the columns have mean 0, this will be the representation for variance. I'm going to look for a vector that would give me the largest of this. And so I'm ready now to formulate that problem mathematically. Okay, so what do I want to minimize? I want to maximize. I want to maximize the variance. What was the formula for the variance? That's what you see in the inner term that's squared, which is what we just described in the previous slide, the third item. And so I've got that expression, and I'm going to do this for all of the data sets, and therefore we would add it up from I to 1. That means all of the data points are taken, and we divide it by n to get an average, right? Among all the phi's that I could think of, I'm going to look for the phi combinations that would maximize this whole expression, subject to the constraint that the weights are tied down so that they're constrained by having their sum to be equal to 1. This is a problem that if I was going to be very careful about the picture I would put on the slide while you were waiting on the cover, I would have put singular value decomposition there. This is a place where I have told you many times where linear algebra shows up in a big way. You might have heard of this. Singular value decomposition is a way to decompose a matrix into 3 products. And so the U and V, the ones that are going to be the two endpoints are the reduced ones. And what you will have as the singular values, the diagonal matrix in between, is what these phi's will now give you. So singular value decomposition is a little bit bigger. It has got some other purposes. Principal components is one kind of singular value decomposition where you have a certain specific nature to the value decomposition, to the SVD you would get. So what we are now getting into is just like what we've seen in when we were talking about random forest and trees. I told you the inside workings of it. We're not going to write an SVD solver ourselves. Our tools would use it. When we call for a PCA in an R tool or Python tool, things will happen and we'll get the principal components. But what is going under it is a singular value decomposition. And that now should also immediately tell you why this is called a way of dimensionality reductions. SVD is a way to do singular value decomposition. It has got its own things about being difficult to compute and takes time, and people would come up with making this faster. There is all kinds of things one can do to make them faster, and sometimes you don't need to compute all of them, and so you would stop when you have enough of them and things like that. But at the heart of it, what you're doing when you do PCA, the way you get these phi's is by solving a singular value decomposition. And we've got some good algorithms, especially thanks to people who've done some good work in the 80s, I guess, where it was. And so we have a way to compute this. So at least we argued for how to get to the first principal component. And we kind of formulated it as a maximization problem of a variance. And that when we looked at the underlying metrics, it turned out to be something that could be solved using PCA. Much like and this would probably take you, and when I get a chance to look at what you responded to hear about your view of PCA, if you have encountered them, what I suspect the majority of this class has had is a class in linear algebra of some kind. And when I told you singular value decomposition, your mind might have gone, if there was a good book you read or a good lecture you followed, a geometric interpretation. There is a very beautiful interpretation of what SVD does geometrically, and we could extend that one to PCA, and it's actually even nicer to see this geometrically in terms of what this values, the loading vector and the loading values that I just told you, would mean when they are seen in terms of geometry. And so what this means is when you have projected the values onto the principal component, the Z1s themselves are the values that are about the projection. So if I go back, if you don't mind me going back, what you get on this toy example I showed you earlier, we have determined that what this green line is the first principal components. The projections of these points onto this line, the values that you would get when you do them, is what these loading vectors would be, the values, the phi1, phi2, and so on would be. That's the geometrical interpretation. And now among all the lines that you could find where this projection is, the variance is maximized, would also tell us what the principal component is geometrically doing. Okay, this was the first. That was how we get the first principal component. Now we want the second, the one that was a dashed line in the curve that I showed you. So the green line was a solid one. That was the first principal component. How do I get the second one? The second one is done exactly the same way as the first principal component was used, except now I'm going to demand that the vector that I would be after is completely uncorrelated with the first vector. Otherwise, it will be telling me similar information. I'm insisting on being it uncorrelated to the extent that it tells me completely different information than what the first one did. Because you remember the green line was telling me, it was capturing a good version, portion of the variation, but it was not telling me everything. So if I needed some other thing that is completely new, then I'm going to insist that the second principal component that I would look at will be uncorrelated to the first. I'll say it in a slide in a moment, but that way of saying it's uncorrelated is to insist that it is perpendicular. So the second principal component would be perpendicular to the first one. And when we go further, we will still insist that the third one will be perpendicular to both the first and so on, if you can imagine a picture of that kind when you think of it. So once I have done that, the rest of the computation would be exactly the same, and so I would get these values, and I would start using. And so that a singular value decomposition now would mean the first one was the first one of the SVD values, the second one was the other one. So I don't have to do these SVDs all the time for each one of these principal components. In fact, I can compute them all at once, and then the values that I would pick, the sigmas, as they are called in singular value decomposition, would be the ones that would correspond to my vectors. So The mathematical equivalent of insisting that it is uncorrelated is to say the new vector, the second principal component now, z2, will be perpendicular to the first one. So if I keep on doing this, then I will get all the principal components. How many can I have? And we will finish this discussion by actually empirically finding out when to stop. But how many can I have in theory? In theory, I could have as many principal components as there are p. That's the maximum you can have. But there are times when you have, like when you do, in big data problems, you may have 10 or, fewer n's than there are p. So you could have lots of feature vectors, but fewer n's, fewer cases. And if that's the case, then you cannot have more than that. The math won't work. And so you will have the minimum of n minus 1, and that has got to do with degree of freedom, and p. Usually, p is larger than n minus 1, is smaller than n minus 1. And so the real factor for how many principal components you would have will be the feature vector, the how many vectors you have p. But if you have it the other way around and you have more features than there are cases, then n minus 1 will be. So the minimum of these two, that's at most how many you will have, but they are in decreasing order of importance. And so you will not need to compute all of them or use all of them. Okay, so we're going to use an example now. And this example is a real data set that was, I don't remember the years, but in the book you would find it, maybe the early 2000s or something like that is where this data set was collected, and it has to do with crime rates and about arrests in the US. And so the crimes that are associated with these arrests has to do with assault, murder, and rape. And this data set also has something around population size of different cities, urban places in the US. And so there are 4 things to consider: assault, murder, and rape. These are the crime types, and the urban population, this is the 4th one. Otherwise, we have data around for 50 states. So our n is 50. Thankfully, now we have p much smaller than n. So if p is 4, n is 50, and so we would expect principal component that could go all the way up to 4. But as we will see here, we will probably be able to explain them with fewer than 4 principal components. And for these data sets, the data is standardized. That means the mean is set to 0. And so the mean of each is 0. And therefore, we just look at the variance to be able to determine the principal components. So this is a figure. And it probably is not big enough for you to follow along. But when you look at the slides or when you read in the book, you'll probably be able to get it. This is called a biplot. A biplot is a very common thing to do when you do PCA. It has got 2 pieces to it. One, it's a plot of things between 2 of the principal components, the first principal component and the second. And usually these are the ones that would tell you the most. As I told you, the first principal component for any data set that you have is the component that tells you the most variation. The second will be the second most important, and it will go on in that way. And so the first and the second, most of the time, either would tell you much of what you really need to know, or even if they are not telling you, like if they are telling you 80% of what you need to know, they still would be helpful way to get a summary in a way. And so to plot them would make sense. So the first principal component against the second principal component, that's one piece of information you get from this. That's one part for why it's called a biplot. The second one is it's also a plot where you see the principal component, the loading vectors drawn on the same plot. And that's what you see with the 4 orangish type of curves that you see. So you've got 2 plots together. And the first and the second principal components, when the data set has got 50, now we'll have a plot or the names of these data sets, the 50 ones, when they are put together in here. So if I now we remember this is US states, and so this, well, it's not projected from 4D to D. Well, okay. Yes, so yes, that's an accurate way to say. So we've had 4 feature vectors, and so now we are looking at them as, the reason I was hesitant in saying yes, Ned, to your question was because this plot is doing more than just visualizing the 2-dimensional first component, second component. If it was just that, without these other orangish or brownish plot, then that would have been a visualization. But this has got an additional thing, yes. So it's reducing it to 2 dimensions, but these 2 dimensions are now not exactly what, it's not two of the four. It's another way to look at them. And so the first principal component, now the loading vectors now will tell us. So if you think about the three features that were used were three types of crimes: rape, assault, and murder. And you can see they are, the loading vectors that are around them kind of tell us they're headed the same way, they're going east to west, whereas the urban population is showing us another dimension to this. And it has probably not so much to do together with them. It is another thing that's about the sizes of the cities or the urban population in each of these states. So you can now begin to see an interpretation. So the three around this one tell us about how much crime rate there is in a state. And so you've got places like Florida and Michigan and so on, where there is probably high crime rate. And then you can see places like New Hampshire, Maine, or South Dakota, and on the lower one. And if you look at the vertical, or the up and down direction of this one, it kind of shows states where there is higher urban population, like California is high, and then you can see like South Carolina and things like that are lower. And so this together, now the loading vectors, they are about the same magnitude. So the lengths of the vectors around the three crimes that you see kind of give us about the same magnitude, the loading vectors, and the urban population one has got a different, but it is on a different dimension of the two, it tells us. And so you can interpret this. The data set that was originally given, I am sure if we were to attempt to plot it, would not tell us something that was a quick summary. This one is. And so now we can talk about places that are high urban population and high crime rate, like California. And there will be places like where there is not so very much high in terms of urban population, but high crime rate, like Florida. And then you can find places where it is low in both cases, like West Virginia, for example, here, or South Dakota. And so now you have a summary of the data set that tells us the two principal components and the loading vectors around them together. And this is a nice way to visually get them. When we finish this, I will also tell you, other than visualization and getting a summary and getting a sense about the data itself, to also help us if we were to use this for a supervised learning problem. And I have made this point a couple times before, but we will finish the discussion today with that one. What I have in this slide is an explanation of what I just showed you, so I'm not going to spend too much time telling you about this. But this is a useful summary you would get. And when we get back to having maybe a lab session, when we finish both this one and clustering, I will probably show you, you can get the values for this one, and there will be one of the summaries you would get if you do an R function to call, for example. And so we've got these four vectors and their values for the two principal components, PC1 and PC2, they are called here. The values that you see, the phi's, the loading vectors, you see them here. And so on the first one, murder, assault, and rape, these were the three crime types, were about equally weighted. That's what the visual showed us. And the values, you can see them, they're about the same. And on the other principal components, which has got a little bit to do with population, urban population size, you can see a couple of them has got negative values, and then the highest value comes to something around where urban population is, loaded up by 0.872, which is what you saw in the picture, going all the way up to showing that length of the vector. And that's what this value is showing you. There is an interpretation when I was telling you about the principal components and looking at them geometrically, where you could find what we just saw now to have a nice interpretation geometrically. And so this is a fictitious data. It's not the USA arrest data I showed you now, but it is a fictitious data that has got some cloud of data points. And this, for the purpose of what we wanted to show here, are color-coded to just show that there is some kind of grouping, some kind of clustering to them. And so you've got these data points. Some of them are green, some of them are light blue, and some of them are brown. Their original space in which they lived was the one shown on the left. And this is how the cloud of points were. And this is three-dimensional. And so you've got the 2 dimensions and the third one coming out of it. One way to think about what principal components analysis is doing to this cloud of data points is to find a plane, this time a 2-dimensional one, the first principal component and second principal component, that would explain this cloud the best way possible in terms of the variance, which is exactly what the first principal component would do and the second would do when they are perpendicular to one another, right? So now if I have insisted that this will be a hyperplane, a two-dimensional one for these three-dimensional data points, and then the plane that captures the best in terms of their variance would be the gridded plane that you see. This is the hyperplane. Okay, when I tell you the point I just made now, some of your minds might have gone to something what we did in linear regression. If these were points, then you would have to find a plane that would kind of be a best way to represent them, and that would have been the least squares, error that you would have gotten. It might have reminded you that, and you're close, except now we don't have y's. We don't have these errors. We don't have the least square errors that we want to minimize. We just have points in the cloud. And what we are looking for is a plane that represents the variance the best way possible. And so one way to think about that plane, looking for that plane, would be to see where should I put this plane so that when I project each one of these points to the plane, that variation is explained the best way possible. Rather than saying, I have an error I want to minimize and I want to get closer to these data points where their errors is minimized. The two are not the same. They may sound like the same. That's maybe the first that came to your mind, but I just told you the difference. If I were able to draw things, I would have shown you what it means. But now what you are trying to find is a plane that best explains. That means when you project these points onto the plane, their distances, when they are added up together, that projection is minimized. And that's exactly what SVD would do. That's what principal components would do. Okay, when you have found that plane now, the two axes that do this, the hyperplane, now you can see how it helps you to visualize it. And now when it is plotted on those two principal components, the data points that you saw now nicely show how they are clustered. And so the points that were deliberately colored like this, fictitiously, synthetic data, now sees clean separation between where the orange ones leave, when the green ones leave, and when the blue ones leave. Well, so whatever it is that these principal components are telling us now has got three clustering groups in a clean way, and you can visualize that now better. And this is the description that I just told you. Okay, I have about 10 minutes. I am hoping, and I really am hoping that you're following me along. And I'm going slowly enough, but I want to point out two things that are very common to do, and make sure that we do them right. One of them was about, I told you, for the math to work, we say the mean of these columns would be standardized, and we could get the data set the way that way. Otherwise, if it's not, when we can turn it easily. But there is another thing we need to do. And this other thing is extremely important because it's easy to forget and people make that mistake. You may have a data set. We've got like this urban population and the crime rates and things like that. The crime maybe would be counted one way, right? They would count whatever it is, right? How many times there are, how many 911 calls there were, or how many people got arrested. So there's kind of a uniform way to talk about them. Now throw into that about urban population, and now you're counting people, and there will be millions, and so the scale is very different. Or you can think about what would happen if you were to go to a store and then you're telling about sales, and there will be some people who would sell milk, and there will be others when you have a TV to show. If you go to a place where everything is sold, and so the amount of how much you pay to get a gallon of milk and what you would pay when you buy a TV is completely different order. And so sometimes when the data sets are of variable scales like that, the information you would get from your PCA could be distorted. And so what you see on this picture is the same data set when things are accounted for in terms of scale and when things are not accounted for in terms of scale. So the unscaled version is what you see on the right. And you see that this urban population is now dominating everything else. And it's not necessarily giving you the picture that will be the most helpful. To avoid that, you would scale them. And by scaling, it means now you would look for having to be free of that variation. And one way to do that is to normalize them in some meaningful way. And sometimes these things are automatically available for you, so you can scale them. In addition to making the mean zero, you can scale them. And now you get a picture like what you see on the left and the right. So that's one of the points that I wanted to tell you. Scaling of variables matters. The other has to do with when to stop. I told you that these principal components are telling us a piece of information at a time. They are uncorrelated. And by design, the way we did them, the first principal component tells us the dimension we have to go for that tells us the most variation in the data, the most helpful thing. Then we say the one, given that, completely uncorrelated, what would be the second one? And that would tell us the direction we have to go to explain the most variation this time when it is uncorrelated to the first. And the third one would go on like this, like this. So now a natural question would come, and we know when P and N are such that P is smaller than N, then we can have as many principal components as there are P, but we would probably not go that far. After all, one of the goals is to reduce dimension. So when should we stop? To answer that question, we say something that's called how much of the variance is explained. And that's called proportion of variance explained. So what I have mathematically written here is to quantify them, because we have done such that the variance, the mean is zero, the mean is centered at 0, then we could have the xij's tell us the variance. And so the variance associated with the feature vector x, or the vector xj now, would be the xij's, they are squared, and we add them up for all the data sets, and we average it by n. And then we do this for all of the p's the xj has. That will be the variance of x. What about the principal component? For each one of for the m's principal component, the variance that's associated with it will be simply, the way we have designed it, simply zim squared, because the mean is centered at 0. We square them up, we add all of the elements, divide them by n. So now we have a way to say what the variance of x is for each one of these I to p, and one of the variance of z, the principal components, that's the m's principal components. Now then, because I have got these quantities, I can look at a principal component, the m's one, and then see how much of the variance in the original data is explained. I've got these two quantities, all I need to take is the ratio. Now, when I have found out, then that will be the variance explained by that principal component. Okay, I have in words told you what these mathematical expressions are saying. The only thing that you really need to pay attention to is that the mean was centered at 0, and therefore what the variance of xj means is the summation, and the variance of what zm means is this other summation, that simpler one. And so the ratio between the two would be what will be called the variance explained, the proportion of the variance explained. So the first bullet point is a recap of what I told you in the previous slide. So when I have this ratio, then I have found out how much of it is explained. These things are plotted. Most of the time, we'd actually get them automatically by a tool, like R would do for you. And there's two different ways to plot them. One is to plot to see the principal component. And so we have that on the horizontal axis, and what we'll have on the vertical axis, I'm going to talk about the one on the left picture now, is to tell me, to show how much of the variance is explained by that principal component. And so we have the first principal component for this data set. We don't really care what this data set was. Shows us that 0.6 of the variance is explained by the first principal component. That's great to know. We will not be surprised to find that. That's a very common thing to see. Half, or a little bit more than half, or something, 65%, or something like that, of the variance is explained by the first principal component. And so that's what you see. How about the second one? The second one, in this particular case, explains something around 0.2 of the variance. 20% of the variance is explained by the third one. What about the third one? That is explaining something like 0.5 out of 0.1. It looks like 10%. And so you can look at them this way, and so you can continue. You could also add them up. How much of the variance is explained by just the first principal component? How about the first two? What you see on the right is that, more like a CDF, right? And so you've got these alternative ways of plotting them. It doesn't matter which way you are looking at, but the first one is probably easier to see because you can see the contribution of each one of them. And the second one is easier to see because now you would know how much you have to go before you say, I'm happy. So because now you can get a plot like this, then you can decide when to stop. And you want to stop when you feel like you have much of the information explained. And so in this particular case, for example, the first two have explained something like more than 0.8 of the variance, and that probably will be a good place to stop. And with the added benefit, now you've got only 2 of them, and you can even visualize them and get a lot of help from it. When I say this now, you probably would have gone, okay, you've told us about cross-validation, we looked at it, and we looked at it, how they were used to decide when to prune a tree and so on. Why don't we use that? Well, the answer is very simple. It's because we are in the territory of unsupervised learning, so we do not have whys. We do not have responses. We do not have errors that we can use to use cross-validation. Therefore, that plot is actually what we need. So this is called a scree plot, by the way, and people would tell you that you would stop when you get the elbow. So think of the picture that you see on the left as an elbow, well, you know, something that would go down. By the way, these points necessarily would have to go down. You cannot have the third principal component explaining more variance than the second, or the second explaining more than, no, it will be decreasing because that's how we were designed. And you would stop when you hit the elbow, when you don't see too much of an improvement anymore. So the elbow here would be at the third principal component. That'll be a good place to say it's where the elbow is. And so that's how you would determine visually, manually, by looking at it, you will determine when to stop. And cross-validation is not a method because there is no supervision. But you could use, this is the perfect place for me to stop and to come back and have circle back what I told you. You may have very well in your projects or in your research, a place where you have to do supervised learning, a regression problem, and you've got too many vectors. And so there is a way, we have learned enough of them to find out which one of the features are important. And you've got a way to determine them. You have to exclude when there is collinearity and things like that. You could do all of that. That is about selecting features that are the most predictive. But if you completely transform your original problem, and now you've got PCA done on it, and you've got some other dimensions, you could use now the new dimensions for doing your linear regression. The disadvantage, or the thing that you need to be careful about, is the original ones are lost. No, so you don't have them. And so you've got some other thing that has come, the latent feature, the guy that, you know, the thing that you looked at a person and you say they are, you know, this or that type of person after you've looked at them. This is the new dimension you have now. If that is good, if that has given you a new insight, now you could use that to do your linear regression. Now you've got a much smaller dimension to work with. When you have found that interpretation correctly, now you can use cross-validation with this one, because you've got responses and because your original problem was a supervised one. So you could use PCA in combination to ultimately solve as a pre-processing step, or the first step for solving a regression problem. In that case, you can now use cross-validation. But the way it was, the PCA, the plots that we saw, the principal components, the proportion of variance explained, the scree plot is the one that would tell you when to stop. But if you use it as a step to do linear regression later on, now you can use cross-validation. All right, this was where I wanted to stop, and we will continue with clustering after we deal with reviewing the topics we have next week on Monday. Let me see if you have any questions for me. This was probably, at least time-wise, I stopped at the place where I wanted to stop, but I'm not sure how much you followed me along. Let me take a look at, did you follow me along? Okay, good. Any questions for me? I'm going to stop sharing.
So will we have a chance to see this in action in R?
Yes, yes.
Okay.
What I would like to do is finish the clustering topics first, and we're going to look at 2 very popular methods to do clustering, and then I will have one session where I would do them in hopefully one. If you feel like, I mean, I am okay if we are one topic short. I'm going to have maybe an abbreviated discussion of time series data mining. That's what's one of the topics left, and deep learning. And I would rather have what we covered done in a good way rather than trying to cover everything. So I'm okay with you know, reconsidering that. But yes, we will have a session. In fact, that probably will be even more helpful to see this piece, you know, when to stop and things like that clearly. Well, the difference between PCA and feature selection is what I was trying to get to. So when you do feature selection, or is you are selecting features from that are existing. So I had P of them, and I chose some of them. And I was very careful in what I did to get what should be selected, because they were the ones that were most helpful in predicting. The features or whatever it is that I get when I do PCA is completely different. They're not there. They're absent. Now we have latent things. It's a completely different dimension. So, and that is the big difference. And it's a very big difference in the sense that we are now dealing with things that you cannot explain back with what you saw. I hope that helped answer your question. Okay. All right. If you do not have any further questions, I want to remind you to do your progress reports. I know some of you have submitted. Today is the deadline. Go ahead, do it. Don't worry too much if you don't have results or anything. And those of you who are 575, you have heard back from me. So go do your survey papers, ration your time, budget the way you find them the most helpful. But we would be doing no more assignments. Project and survey paper is what you would focus on for the remainder of this semester. All right, there are no more questions. I'm going to stop here. Have a great weekend.